there we just plot graphs. Okay, so we plot a graph to understand how the model is performing. This is for binary classification. Okay, binary classification. Confusion matrix can be for any number of classes. Okay, it can, the number of classes can go on increasing, but this is generally for binary classification. Okay, so we have, so these are graphs. So binary, so we'll put one parameter on one axis, other parameter on other axis, and we'll measure. So what are the, on what is there? So let me move this to the other page itself, and then this will make sense. Let me stretch it a bit so that it becomes clear. Okay, so say this is your graph. So on the y-axis, so what are we plotting here? So it is a curve, it's a graph that we plot. Okay, it's a plot or a graph to understand the models, a binary classifier performance. Okay, we have done models performance on binary classification task. Performance. Okay, so this is y, this is x axis, but what is there actually? So y axis has true positive rate. So I'll write it here. So y axis has true positive rate. What is true positive rate from here? So true positive rate, we know that is your, out of all the truths, how many? Okay, so this is your true positive rate. Out of all the truths, actual truth, how many was the system able to actually identify as true? So this is your true positive rate. So actual what was true, of that how many the system was able to identify true. So this is your true positive rate. So y-axis is TPR, that is TP by TP plus false negative, that is true positive plus false negative. This is on the y-axis. And on the x-axis we have, we have false positive rate. Okay, this is your FPR. And how is it defined? False positive rate, this is your false positive by false positive plus true negative. So this is, so y-axis is coming from here and the x-axis value is coming from here. So this by sum of this and this. On y-axis, true positive by sum of these two. False positive on the numerator and the sum of these two. So if you plot these graphs clearly, so you will have, so we have precision here, recall here, okay, and the true positive rate here and the false positive rate here on this. Okay, so we have these values and we plot this on this x and y axis. So here we have true positive rate and this side we have false positive rate on the x axis. So what do we do here basically? So whenever we have, so if you know a bit of machine learning model, so output for binary classification model is a probability score. Okay, and then we have a threshold. So generally the output for model is a probability, so it will be in the range of 0 is less than equal to, the probability is less than equal to 1, in the range of 0 to 1. So the model outputs are some probability of that being. So for example, if I'm doing a cat dog classifier or even never shirt jacket classifier, so it looks at the image that it has and will give you a probability of that from 0 to 1 I am having this confidence that this will be a shirt. Similarly for jacket, okay, it will give a prediction score that this is the, or say for example it is saying that for some prediction it's saying that with 0.8 probability this is a shirt, and for some other image it is saying that that I only have 0.3 probability that this might be a jacket. So we have these values for certain images, and after that we fix a threshold. Generally by default it is 0.5. So this is your threshold. So if the probability value, this p value, okay, if this is greater than whatever p the model is predicting, if it is greater than equal to your threshold, which is in our case 0.5, then this will be classified as one class. Say for example short, this is 1, this is 0, this is binary classification. Okay, so I classify it as 1, and if it is less than 0.5, then I classify it as a 0. So whatever is my threshold. So for this jacket, for something to be classified as jacket, it will just I will just focus on whether it's shirt or not, with what confidence I'm predicting it. And for the jacket, it will just say that it is 0.3 probability that it is a shirt. So this will automatically be classified as jacket. If it is not shirt, then this is a jacket only. If it is not 1, then this is 0. Only 2 options I have. So that's why it is a binary classification. Okay, so this will be classified as 0 because it is less than 0.5. So this is how we do. These thresholds are 0.5. Generally, it varies depending upon our requirement. Sometimes we have 0.6 or 0.7, whatever. It depends on the use case. But mostly, for our practical purposes, we consider this as 0.5. Okay, I hope that is clear. So this threshold depending upon how the model is predicting. So now, when we are doing the actual classification, say for example, I have one patient. Okay, and let me see the example. Say for example, I have a patient and then I am classifying it as a true false. Okay, so this that will be easy. So whether a has diabetes or not. So has diabetes is 1, not is 0. No diabetes. Okay, no diabetes. So I have a test to predict this. So if it has a diabetes, with what or a no diabetes. If it is greater than the threshold of that test, then this will be diabetes. If no, there will be some like kind of sugar in the blood, right? So that test is being done, and then if that is less than that threshold, then it will come to be 0. For us, let that be 0.5. So we have a data, say we have a patient ID, and then we have the true label, that is the final label that we have, and then we have the predicted probability. So what is the true label? Finally, we don't need this these probability values, right? We finally need it as 1 or 0. We want to know whether whatever the test value comes, it will come in the range of some range, right? Some value. But after that, I only want to know whether it has diabetes or not diabetes. That's what is my final binary conclusion. This is what my test is for. Say for example, patient ID 1. Okay, the true label is 1, and the predicted probability for diabetes is 0.95. This is generally called as y hat. Okay, and this is your predicted label is yi, and x is the input. So I have 1, 2, 3, say 5 patients are there. So true label is 1, 0, 0, 1, 1, 0. So 1 means has diabetes, 0 is no diabetes. And the predicted probability with which this came, okay, that is 0.85. This is actual. Okay, this is actual. This is the actual. This we know, but this is another test. Okay, which is the model is giving me. This is actually whether the patient has the diabetes or not, we know, but we are just verifying whether the test is model. How is the model performing? Because always the model will be trained with some known data. So this is a known data. This is the ground truth. Okay, I know this for sure. And then I'm checking what is the model predicting and how good is the model predicting. That's what I want to see. I want to see the model's performance. This is your model's performance. Okay, whatever algorithm we have given. This is the ground truth. Okay, so this is your 0.85 probability. Then we have, say for example, this is for 0.70 probability. Then we have 0.45 probability, and then we have 0.20 probability. Something like this. Okay, so we have these values. Okay, this is true label or actually whether the patient has or not. So now what do? We have this data for receiver operating characteristics. So how do we plot? So we have to calculate true positive rate and false positive rate. Here if we have one data, so we'll get only one data point. But I said it is like a curve. We'll get a curve like this. So we should have multiple data points. Right? Generally it's a curve. So this is like this one line. You will get a curve like this, some curve. Okay, but if I get a true positive rate, a false positive, because I can count all the ones, I can count all the zeros, that will come to only one point. How do I get many points to plot the curve here? So what do we do here? So what's the algorithm? So what do we do? So algorithm here is sort this. We have already sorted this. Okay, sort the data in descending order of probability score. So first thing is sort the data in descending order from largest to smallest, descending order with respect to your model's probability score, whatever probability score it is giving. So sort the data. We have already sorted this. Okay, and then what do? We set each probability score as threshold. So earlier I told you, right, it can be 0.5. But what we do now, we set each probability score as the threshold, and then we try to classify. If 0.95 was the threshold, say for example, then only, okay, anything above this is diabetes, say for example. So only this will be classified as 1, rest all will be 0, 0, 0, 0. If this is my threshold, 0.95. Now if I set my threshold to 0.85, this and this will be 1, this will all be 0, 0, 0, 0. Similarly, if I set my threshold to 0.7, this will be 1, 1, 1, this will be 0, 0, and so on. I hope you get the idea. So I'll set each value as a threshold, and then based on that I'll give my final label, predicted label, and then I'll plot. Then I'll calculate my true positive rate, false positive rate. Earlier this is the actual thing, but now you see the true positive rate and false positive rate will change. Here if I put 0.95 as my threshold, I'll have only 1, 1 and all will be zeros. My true positive rate will be less. If I set 0.545 as my threshold, I will have 1, 1, 1 here till here, and this will be 0. So I will have 4 positive, okay, and only 1 negative. So my true positive rate will increase. So this is how we are getting. So for each threshold we calculate, we set each threshold as each value, each probability score as a threshold. In the second step, set each probability score as threshold, and then a threshold for classification as of for one, or whether it is 1 or 0 or positive or negative class, and calculate my TPR and FPR, because that's what will go on my x and y axis, and each points will get, sorry. So we'll calculate TPR and FPR for every threshold. Okay. So for example, I have, so whatever I have said, I'll just write it on the next page. Say for example, 1, my threshold is equal to 0.95. Okay. So I'll calculate TPR1, FPR1. Okay. Then my threshold will be, for this is for step 2. Okay, step 2 only. 0.85. Then I'll calculate TPR2, FPR2. So these are different points. Okay. And then like this, I'll calculate TPR n, FPR n for n points, and then finally now I have n pair of points, one from y-axis, one from x-axis, x-axis, y-axis, other way around. Okay, and then I can plot this on my coordinate system or on the graph. Okay, and finally we can plot this on a graph. And let me copy this. And then you will get a curve like this. So you will get a curve like, let me draw one. Something like this for where 0 is 1. Okay, so say this is 1. This is 1. So this is y is equal to x. Everything is same. This is your, so this is y equal to x. This is 1 and this is 1. So this is your, any random model can predict this. If I randomly classify all of the labels as 1 or 0, then half of them will be 1, half of them will be 0. So after that, when we calculate this will be my, I'll get just a straight line where half of it is means all the true positive rates and false positive rate will always be same, because randomly it will classify half of them as positive class and half of them as negative class if I have just a random model, because it will do 50-50. And then anything better than this random model, say for example, if I have this curve, the true positive rate is there. So what will be the best model? First let's understand that. Okay, so what should be ideal true positive rate? So my true positive rate ideally should be 1 and my false positive rate should be 0, right? That's how it should be. So ideally my curve should be here. So I should have some, let me draw like this. So I should have, my graph should be like this, that my model is predicted perfect. It has not given me any this is a perfect model. Okay, it is not giving me a probability of 0.95, 0.85 like that. If it is a correct thing, it will give me a probability of 1. Okay, if it is a it has predicted, it is a perfect model, it knows, it will not give me a probability of 0.95. It will always give me 1 for the positive class and 0 for the negative class. So when I set threshold as 1, everything, all the true positives will come together, and otherwise if I set threshold as 0, everything will come as false positive, right? So my true positive rate will be 1 always, and my false positive rate will be 0 always, because everything will be correctly classified. So I'll get this point, because this is your 0 here. Let me come back. Okay, this is your 0 here. So this is your x is 0, FPR is 0, and true positive rate is 1. So this is your perfect model, but that is not happening. My model will not be giving like perfect 1 and perfect 0 probability output, because there will be some confusion always, and there will be some gray area, because the images may not be clear, and definitely even we get confused. So this is the ideal case we should have. And anything, this is a random model. Randomly, if I classify 1 0 1 0 1 0, half of them as 1, half of them as 0, then you'll get this line. Okay, anything better than this, so this is your worst model. Anything below this, we'll talk about this later, it will not go there. So this is your worst, this is your best. So anything in between this will be your good model. So let me draw one more, maybe something like this. So for each of the points that TPR1, FPR1 we are calculating, right? So we'll get these points here. Say for example on this line, so you will have these points like this, and then it's all the points. So this is like TPR1, other way around, right? FPR1, x-axis will come first, comma TPR1. Then similarly, like this will be TPR, other way, FPR, some kth point, and then TPR, kth point. This will be here, and then this you will come here. This will be some FPR, nth point, and TPR, nth point. So for all the thresholds, for each threshold, whatever you have calculated, we'll keep plotting it, and then we'll get a curve like this. Okay. And I said that this is your worst model. Anything cannot be worse than this. If I randomly put 1 zeros, so I'll get this half of them as positive and negative labels randomly. If I put my true positive rate and false positive rate will be equal, this is the worst that we'll get. You can do the maths and check and say why can't we get something like this? Because if you see, if I'm getting something like this, then that is coming like true positive rate and false positive rate. So if I flip the labels, if I make positive as negative and negative as positive, then will this not curve anything that is coming? This will just shift that the other way around. The true positive will become false positive, and this will just shift the other way around. So means whenever you're getting something in this zone, means you can just flip the labels, that whatever is your positive label, make it negative and vice versa, and then this curve will automatically come on this side. I hope the receiver operating characteristic curve is clear. And this area, ideally, okay, this area under the curve, okay, this area, this is your ROC, this curve, okay, this is called receiver operating characteristics. And the area under this, so area under ROC is also called area under curve, AUC, or AUROC. So whatever is the area under this curve, okay, this area, if this is the case, then the complete area will be there. So this area is called as AUC, or area under ROC curve. In short, AUC, area under curve, area under receiver operating characteristic. I hope AUROC is clear. Okay. And the random models, because it will randomly classify everything as half of them labels will be classified as 1 and half of them will be classified as 0. That's why you will always have the true positive rate and false positive rate will be equal, and they will be on a y equal to x axis. So this will be like half. Okay, so but this has limitations, and we'll understand it with an example. So ROC is not the right. Okay, just note it that ROC doesn't work well with imbalanced data. ROC does not work well, or it does not give right output with imbalanced data. What is imbalanced data? Imbalanced data means I have more data from one class than the other class. That is imbalanced. If I have equal number of samples from positive and negative class, okay, then it's not a problem. But if I have lot of samples from the negative class and very few samples from the positive class, then it is a problem. That is called imbalanced data. And because of the formula for the false positive rate, which is your, what is the true positive rate and false positive rate? So just remember this. Okay, what are we plotting? Because of the formula of the false positive rate, this is the problem. I'll give you an example and it will become very clear. So whenever we have imbalanced data, ROC doesn't function well. And let's understand what is an imbalanced data with an example. Say for example, you have a fraud detection system. Okay, so whenever you have a fraud detection system, for example in the bank, what are fraudulent transactions? Okay, you have fraudulent transactions. So the number of fraudulent transactions will be very, very low. Compare it with the number of transactions happening in the system. The number of fraudulent transactions will be very low. Okay, that's what is the imbalanced data. For example, if you have millions of transactions, out of that maybe 1% is fraudulent and 99% is a normal data. But 1% at the bank scale is also a big loss if the amount involved is high. But the number of transactions, if we compare, the number of transactions will be very few. So that's the imbalance we are talking about. And we will see how with the numbers that why this, because of this false positive rate, the way it is calculated, ROC doesn't work well on imbalanced data. Okay, so let's do a fraud detection system with n is equal to 10,000. I have 10,000 transactions data. Okay, and we have fraud entries as 100 and not fraud is 9900, right? Yeah, 9900 plus 100 is it's 10,000, right? So it's 10,000, 10,000, right? So this is your fraud. So let's again plot it the way we do it. So this side it will be your actual, this side will be your predicted. That what is my model predicting? The fraud detection system. Okay, so let's write here. So this is your actual fraud, and this is predicted fraud, and this is predicted not fraud, and this is your actual not fraud. And let's draw the lines. So for example, this is your actual fraud, actual not fraud. So say these are the lines, and we have that what are the values we got? That we have total 100 frauds. So actual fraud are total 100. So this is 80 and this is 20 and this total is 100, and the not fraud is 220 not fraud here, and here the remaining 9680. So as I mentioned on the diagonal, whatever, if it is for actual fraud, predicted fraud, no problem. Actual not fraud, predicted not fraud, no problem. This is very good. Okay, so these diagonal entries are fine, that whatever is actual, that is detected by the model also. So these are your true positive and this is your true negative, no problem, these are good. This is your, actually it was not fraud, but you predicted it as fraud. So this is your, if fraud is a positive label, then this is your false positive. So this is your false positive, and similarly this will be a false negative. Actually this was a fraud, but this, your system was not able to catch it. It said that no, it is not a fraud. Okay, So what is your true positive rate here? So what does it plot? This, let's calculate this. So once we understand how to put this true positive, false positive, so just putting in the formula is simple maths. Okay, so what is the TPR? That is true positive by true positive plus false negative. So this is your 80 by 80 plus 20. So this is fine. This is your 0.8. No problem. What will be your false positive rate? So this is your false positive plus true negative. So this is your 220 by 220 plus 9680. So this will come approximately, this will be equal to 220 by 9900, and this will be approximately equal to 0.022. 0.022. And here if you see that if something is very good, if the model is functioning, all the points, okay, everything will be done perfectly fine, and all my points will be for a perfect model 0 1 0 1, everything will come here only. And if for some worst model, all the points will come here like that. Okay, so the further away from 0 and closer means if the true positive rate is high and the false positive rate is low, then that is a good point and the model is functioning well. Right, that's the measure. That's the measure here. So let's see. So this is a 0.000. So what will be my ROC point here? What will be the ROC point? If I put it on the curve, ROC point will be equal to my false positive rate, that is on the x-axis, comma 0.8. So this will be somewhere on the top left corner, as I mentioned. That means top left corner means it is somewhere on the top here. 0.8 is here and 0.022 somewhere here. Means my model is performing really well. If I plot, if it continues here, the model will give me that okay, it is performing very well on the model, on the given data. Okay, and this will tell that okay, the model is performing very well. But let's see. Here also you can see that the actual predicted fraud. Just check that. So what will be the precision of this model? That is, what is the precision? If you remember, that is true positive by true positive plus false positive. As I mentioned, it is here on this line. So true positive by true positive plus false positive. Okay. So what will that be? What is the precision of this model? That is 80 by 80 plus 220. That is equal to 80 by 300. So that will approximately be around 0.266267. Okay, so this model has such a poor precision. Out of 300 frauds, okay, it is only able to predict 80 as fraud. 220 it is not able to catch as fraud. It is telling that no, it is not a fraud. So that is so much of loss. So the precision of this model is so bad. And that is because of the data imbalance. If you see from this perspective, because this number is very large, the false positive rate will always be very small, and you will see that okay, the points will always be on the left side. This will be very close and it will go very high on this side. Okay, it will never come on this side and it won't go down. So because of this imbalance, okay, which is pulling the values of false positive rate to a very, very small value, and this imbalance is causing all the problems. And that's why ROC is not so good for imbalanced data. I hope that is clear.